It has been shown in the literature that effective image-based relighting of scenes with unknown geometry can be achieved through linear combinations of a set of reference images. For relighting static objects, these reference images are most often acquired by single light sources. In the video, we show an example of this acquisition process, where the bright grid square represents the light that is turned on. Images under new illumination conditions are generated combining the reference images, properly weighted according to the brightness of each particular light of the new pattern. However, this methodology is inefficient in that it requires many more reference images than are necessary to achieve the desired quality in the relighting results. Furthermore, for relighting sequences of moving objects, we need to align all the points in the reference images. Therefore, as the number of reference frames becomes larger, the alignment becomes extremely difficult. Since the placement and brightness of the light sources can be controlled, it is natural to ask, what is the best way to illuminate the scene in each of the reference images? In this paper, we show that it is not using a sequence of single-point light sources, but rather to use a sequence chosen from a basis of light patterns, each composed of many compact light sources of varying brightness. In this case, we are able to illuminate the object by a lower number of light patterns. Once the reference images are collected, they are all aligned with respect to a common coordinate frame. Note that now the alignment problem is highly simplified because it involves a reduced number of images. Finally, the image of the object under new illumination conditions is approximated by a least squares procedure. In our work, we are concerned with the selection of the optimal light basis used to generate the reference images. One possible choice could be to select a light basis independently of the object, for instance, the first terms of the spherical harmonics basis or the first terms of a Fourier basis. Nevertheless, these bases are not optimal in the sense of maximizing the relighting results with a minimum number of terms. We propose the use of an object-dependent light basis instead, which is determined as a simple calibration procedure before acquisition. In order to compute this basis, we first acquire the images of the still object illuminated by single light sources. Then, we compute the singular value decomposition over the matrix of images. The optimal light basis will be the right eigenvectors, properly offset and scaled in order to make all the values positive. The proposed lighting basis performs much better than single-point light sources or even than other object-independent lighting bases, and allows the relighting with a reduced number of terms. For instance, in this image we compare the relighting results of a synthetic sphere using 4 terms of the spherical harmonic basis and 4 terms of the optimal lighting basis. The optimal light basis clearly performs much better. Similar results are obtained when comparing with the Fourier light basis. This other example corresponds to one frame of a sequence of a moving synthetic face. If we observe in detail the appearance of the forehead, we will appreciate how, in using the optimal lighting basis, the real shadows are better reconstructed. For the experiments with real data, the basic elements of our setup are a PC-controlled projector and a color camera running at 30 frames per second. Patterns of light are projected on a white wall, which illuminates the object. This is synchronously captured by the camera. The advantage of this setup is that it is easily scalable, allowing us to relight from small objects to general scenarios. Next, we will show how the reduction in the required number of reference images using the optimal lighting basis allows the relighting of video sequences. In the first example, we relight a tennis ball. Here we show the original sequence where the video on the right represents the optimal light patterns used to illuminate the scene. In a post-processing stage, after aligning the frames using an optical flow algorithm, the sequence can be relit as many times as desired. For instance, here we relight the tennis ball with a moving point light source that smoothly changes its color. The second example shows the relighting of a moving face. Observe the flicker in the original images caused by projection of the optimal lighting patterns. Now we show the relighting results with a white moving point light source. With our method, we can adjust the light directions, strengths, and colors in any manner that suits us. For this example, we have also relit the scene with the illumination acquired in Times Square. Note how the abrupt changes in the environment illumination also induce sudden changes to the face appearance. In the last example, we show how our setup is easily scaled and allows us to relight bigger scenes. This video corresponds to the original sequence illuminated with the optimal light basis. Now we relight this scene with a moving single light source. Notice how the cast shadows change with the movement of the light. Here we simulate how the scene would be if it were illuminated by the light of Times Square. Finally, we show that the method can be used to adjust the lighting locally. Here we simulate a green spotlight on the face and a blue spotlight on the cup. The white and diffuse source illuminates the background.